So Jorge, thanks. Chatting again. Last time we spent a lot of time talking about mass. Mass. And this time we're going to tie that in with density and buoyancy. Because if you're measuring methane or other greenhouse gases at the perimeter of a facility, you have to trace their path backwards in order to understand where they came from and quantifying them. So buoyancy is a big component that will tie in with that.
Yeah, and I have some good news and some bad news for you. The good news is that we're going to move on to different topics. The bad news is that we're always going to talk about mass. Because we can't not talk about mass. We have to talk about it. So going back to what we talked about last time, conservation of mass is the constraint that we're bound to. That's the thing that enables everything that we do in terms of technology. It's the mathematical principle that guides every single decision that we make in terms of how we model gas, how we model dispersion, how we lay out our sensors. Everything has to do with conservation of mass. But there is energy as well. There is energy and there is motion in the atmosphere that depends on mass and energy in the interactions between the two. And we're going to talk about that. One of those is buoyancy, how buoyancy manifests itself and how that changes the way methane might disperse itself around a facility.
Let's go all the way back to the beginning. Obviously, again, we're always going to be talking about mass, to your point. But density and buoyancy, just what is it?
Okay, so imagine in this space of air that I have right in front of me, for some reason, and we're going to talk about that reason later, for some reason, a certain space or collection of air molecules within that space becomes a little bit hotter, becomes energized somehow. Let's say, for instance, that I lit a match right in that very spot and heated the air right around there. Well, what that causes is it causes the density locally, the density of that air to decrease because it wants to expand. It becomes more energetic. So the little molecules inside of that little bubble that I'm creating are becoming more energetically. They're pushing each other out a little bit. That little bubble becomes less dense than the air around it, and so it spontaneously begins to rise. Now, you might think about those balloons that I had last time, right? And I was, using this idea of parcel theory. Parcel theory is very nice for visualizing things, in a tactile sense, but it doesn't really get at how things really move in a fluid. So if you look at this, little simulation that I have, here's my bubble that I've made that is sitting in air, the yellow stuff around it, that is more dense than the air that has been heated somehow, right? When we're going to talk about how things might be heated, rather than just lighting matches around or doing things like that, but things can become heated or somehow less dense than their environment. And then the bubble begins to rise. Initially, it begins to rise as if it were a solid balloon. But then other things begin to happen. It begins to spread, deform, and curl up onto itself and induce motions that are circular. So always circulations. Circulations is the way that nature moves fluids around is by circulating them. And so circulations begin to develop on the outer edges of the bubble. The top of the bubble actually sees a little bit of convergence, which begins to accelerate it a little bit faster, because you have convergence of that hotter stuff that's beginning to move. And you get smaller circulations that begin to develop on the outer edges of this bubble.
So to this point, let's break this into two parts, this diagram that you have here. Let's talk about the edges and what's happening there, and then the convergence that's happening there at the top.
Yep. So let's talk about the circulations at the edges. So that is happening because you have large differences between the red stuff and the yellow stuff. And because you have large differences between the red stuff and the yellow stuff, remember, motion is still being driven by changes. Motion is driven by changes in density. So these big density changes between the red and the yellow drive what we call convective motion or advective motion. Nevertheless, because you have those changes, motion happens spontaneously, and it happens in a circular fashion because, remember, when I did the balloons, when one balloon displaces, another one has to rush in to replace it. So if I have some piece of air that's moving or some piece of this bubble that's moving relative to the other stuff, some stuff has to rush in to replace it. And you develop these eddies and these circulations. And this collection of eddies and circulations is what we understand as dispersion. This red stuff is now being dispersed around in this medium by this spontaneous motion of the bubble. Notice how the bubble starts as this coherent circular blob and then begins to spread and untangle itself and sort of occupy more of the space, and it disperses. So this is how dispersion happens as a consequence of buoyancy.
And then the convergence, right? It seems like at the beginning you see the flattening out of this dome.
Yeah.
What is happening there at the very end of the frame where you're almost seeing it come together and it's increasing in density yet again?
Right. So notice how the bubble spreads outwardly laterally, right? The bubble spreads laterally, but you have this what we call filamentation. It's a fancy term for things becoming thin and concentrated. So you have this upper edge of the bubble that's becoming concentrated. It's actually converging in the vertical direction towards the tip of the bubble. That actually concentrates this difference in temperature. And by concentrating the difference, you have more difference, more motion, faster, more energetic. And that's why you see at the very end of the simulation how the top of the bubble begins to sort of accelerate a little bit. So it's even more dispersion. The bubble eventually will separate and break apart, and the lateral pieces will move in one direction, the top piece will separate from the other stuff, and you'll get the red stuff, so the concentrated stuff. You can imagine it's a methane bubble. You get this methane bubble that now is beginning to disperse around in this particular little box where we've run this simulation.
And so let's talk about the why, right? There's a lot of reasons that this can happen.
Yeah.
You can have chemical buoyancy,
right,
which is really pertinent to what we're doing a lot with methane being more buoyant than the vast majority of the compounds in the air. You can also have energetic buoyancy. You see Oppenheimer is a hot movie right now. Anyone who looks at that says like, wow, that looks like a mushroom cloud. I don't necessarily think a lot of people know that there's an incredible amount of heat that's generated in an atomic explosion. So much so if you look at it, it'll actually burn your retina. It's that bright. It's that energetic. So can you unpack this a little bit more in terms of the drivers of this buoyancy, in terms of the changing, either the difference in density or the changing in density that causes this to occur?
Sure. So density locally can change by in at least two different ways. One, it can be more or less concentrated mechanically, meaning I can actually move masses around and concentrate them to make areas more dense and other areas less dense, and that drives motion, right? And that's kind of what the wind does. The wind pushes things around, concentrates things by way of a particular physical quantity that we call divergence. So the divergence is how when things spread apart or come back together. So convergence being the opposite of divergence, but typically we just say divergence is either positive or negative. So you're either spreading apart or you're coming together, right? And the wind tends to push, methane around and concentrate it or, dilute it locally in areas, creating these kinds of situations, these kinds of, bubbles that are either less buoyant or more buoyant. And if they're more buoyant than air, then they rise relative to the ground. But if they're actually less buoyant, all I have to do is flip this over and they actually plummet down to the ground. So they have to fall relative to gravity because gravity is always there. And so buoyancy is something that happens relative to the gravitational pull on the ground. And so things either float relative to gravity or sink along with gravity, depending on their density. Now that's one way, right? By concentrating mechanically, assuming that everything's at the same temperature. Now let's imagine that we have no wind. So the opposite scenario, we have no wind, a perfectly still atmosphere, but we can somehow energize pockets of the gas, right? Now we're creating bubbles that are less dense or more dense because of heating. where we can either cool something. So let's say we can stick a little lit match in one place and an ice cube in the other place, and we can cool air locally or methane locally in one place, but also expand it in the other place. Now you have a bubble that rises over here and falls over there. So that's another way in which you can change density. So you can either change it mechanically, or you can change it by injecting bulk energy into an area and causing that to expand.
Nice. And so
contract.
What about like the chemical difference, right? What is driving that? And explain that in a little bit more detail.
Okay, so there's always going to be between different gases. Different gases have a different sort of natural density to them because they're made up of different stuff, and they arrange themselves in a different way. So if you think of two gases at a different temperature, say air. Air is a mixture of gases. It's got mostly nitrogen, a bunch of oxygen. And nowadays, it's got a lot more stuff that we'd like for it not to be there. So that's part of what we do, trying to remove some to get back to the air that we evolved in. And then you have pure methane, so CH4. So 1 carbon, 4 hydrogen atoms. It arranges itself at a particular temperature in such a way that it is actually lighter than air at that same temperature, just chemically speaking, just by virtue of the fact that it's made of different stuff. So that difference is always there. Now, the energy and the convergence of masses and all of that stuff plays a role, but it's always going to play a role relative to that sort of native difference between the two chemicals. So at the same temperature, the methane is always going to float a little bit. But let's say I were to cool it, I can cool it to such an extent that I'd make it perfectly in equilibrium with air, right? So I can sort of get back that difference if I want to by cooling that methane some. And so those are the three factors: A, the chemical difference between the gases; B, divergence and convergence of masses that can create differences in density; and C, changes in temperature locally that can create literal cold or warm bubbles of the stuff.
And so I think it's important for folks to start to think about how a lot of these are occurring simultaneously, right? So like, let's bring it back to the practical. Oftentimes we're measuring methane emissions at an oil and gas facility.
Yeah.
As the methane comes from thousands of feet below the surface, many times, but not always, it's warmer coming from that deep below the earth.
Mm-hmm.
So as a result, it already has more energy. Then we have the chemical buoyancy parameter as well.
Yeah.
And then we have the velocity of the release, which we won't talk about here, but that's another important piece as well, meaning it's coming out under a higher velocity, and that's a factor as well. This then gets overlaid in terms of the whole wind pattern that's existing there at the facility as well. So now you have all of the turbulent flow that may be occurring at the facility that's layered on top of these different factors for the buoyancy. And all of these forces plus more are pushing and pulling at the exact same time. Is that the way to think about it?
Yeah, absolutely. And they're all doing it simultaneously, right? So all these things are happening simultaneously. It's not, we tend to organize these things in sequences because that's what helps our brains. But in reality, all of that is happening simultaneously. So let's say the gas, let's imagine gas that's in a pipe, right? That pipe is connected to the underground. The gas is hotter. Let's say that it's hot somehow. It has some amount of energy associated with it. Maybe it's been even compressed as it's been transferred around and pushed around those pipelines. And then there's a leak, and that gas begins to emanate into the free atmosphere. At that point in time, if we were able to go to that specific leak and take a bunch of readings of the temperature and the pressure of that particular gas and then the air around it, we would be able to establish what the difference is. What is the difference in density between the two at that particular moment? And then things begin to change. Then things begin to evolve. The wind comes in, picks that gas up, and begins to carry it around. And maybe there's another leak somewhere else that's on a pipe that's right adjacent to that. And some of that gas gets picked up and gets shoved into the gas that came out of the other pipe. Now you have some convergence. So now that stuff might have gotten a little bit heavier. But it was hotter to begin with, and it's being picked up by the wind. So there's everything is going on at the same time, which is the reason why we employ simulation technology.
And the reason this is important, just to help people understand is like one of the things that people will talk about, well, the controlled release facilities, right? Where you release methane into the atmosphere. But as we're talking about here, like the energetic component is important, right? To understand how much energy is actually in the gas itself. And one of the things that we see at the controlled releases, one of which we were doing out in the desert, they were using LNG, which is very, very cold, right? Sub-zero. And so that's coming out at actually a colder temperature, far colder than the air oftentimes, compared to the natural gas that comes from beneath the surface that's often hotter. So a lot of times people will be talking about, hey, these controlled testing scenarios, but nothing is perfect. And oftentimes these controlled release settings miss something. And in this case, many of them miss the entire energetic component, or oftentimes can even go in reverse, meaning that they're depicting a situation that may not actually line up with what's happening in reality, where many of these methane releases are coming, obviously, like I said, from deep below the surface. And so they're more energetic in nature. I guess a thing to take a step back, like why this matters in terms of numbers, right? Mm-hmm. Can you help people get a sense, because you did a lot of great work with some of the other folks on the team, looking at, okay, if we do take buoyancy into account and we don't take buoyancy into account, all else equal, we're using the same quantification model. What sort of differences did you see in that? I know there's been some stuff written, but just help people understand like how much this can drive the output in terms of quantified emissions. And if you don't pay attention to this buoyancy and, you know, obviously the chemical buoyancy, the energetic buoyancy, how much you can possibly miss the mark.
So I think we need, rather than just talking about buoyancy, we need to talk about the vertical structure of something like a plume of methane, right? So we imagine that methane is being dispersed as this coherent thing that we call a plume, and some of that is true, right? If you look at smokestacks from factories around town, you see plumes that are a little bit jagged or broken up, but more or less they look like these coherent objects, right? And they're being blown around in the wind. So if you only think about how it's being blown laterally in the wind, then that almost certainly assumes that the stuff is going to be located almost entirely at a particular elevation, at a particular plane, right? And so if you happen to have a sensor that's mounted at some height and it picks up this perfectly lateral plume, and you assume that it's picking up the core of that plume, then the way we do this inversion modeling, or the way we ask the question, hey, given this concentration here, how do we know what the release was over here? If I assume that I'm picking up the core of the plume, the very, very center of the plume, then that determines exactly what leak rate I should be looking for. But if that plume has moved vertically somehow because of buoyancy effects, because it got ejected at a particularly, at pressure, at some velocity, and the plume is actually, the core of the plume is actually over here, and I'm picking up just the very edge of it down here, and I think that I'm picking up a small concentration, but I'm still assuming that I'm picking up the center of it, then I will back out a much smaller leak rate, something that is far less than what actually came out. And that's the one thing that we don't want to do. We don't want to underestimate due to these things. If there's a physical reason for that, then we need to account for it and not underestimate it.
Yeah, and I guess we'll have a follow-up discussion on this, but the first time I started exploring some of the math behind this and seeing the outcomes, it was startling to me, meaning that the same release point and the same monitor downwind of the release point, let's say it's 10 ppm, and this is the example I always like to use. If that monitor is reading 10 ppm, there's actually two answers, right? It could have been a roughly 3 kilogram per hour release, and you're catching that, center line of the plume, or it can be 114 kilograms per hour, and you're catching that edge like you just hit on. And so I say this because I don't think people understand how much that buoyancy and the nonlinearity it can create can shift the quantified emissions. 3 to 114 for the exact same concentration on the same monitor downwind, all else equal. And so it's shifting that. I think that people haven't really appreciated up to this point, because folks, either through modeling or through prior knowledge haven't really had the ability to tackle this. And I think that's a good segue into like, why then has this not been done or considered at scale more, given how dramatic the ramifications of ignoring or trivializing buoyancy can be? Explain some of the problems as you start going down this route with buoyancy that you can encounter.
I'm going to give you my personal opinion, and this is my personal opinion as a scientist, but in general, in the engineering discipline, in the applied sciences, we're afraid of nonlinearity, and we should be, because it's one of the requirements of an engineered system, of a system that you, especially one like the one that we're trying to craft here, where it's a predictive system for quantifying emissions, right? So there's a certain requirement for reliability, for robustness, and for control that comes along with the desire to create such a system. Nonlinearities tend to act against those requirements. And so it's very difficult to incorporate a true nonlinearity into a modeling system without invoking things like multiple solutions to things, and other kinds of, they're not pathologies, but they're just natural consequences of looking at, these nonlinear effects that are problematic when you're trying to make an engineered system, right? And so that's why people haven't done it. And it's difficult, right? Now, we understand the importance of buoyancy. And you mentioned that there are two solutions. It's not that there are two solutions. There's one reality that we're after. The reason this multiple solution situation manifests itself is because when you don't take into account the correct physics, you have to invoke an assumption in order to account for that missing physics. And when you invoke that assumption, that's when you introduce that problem of the multiple solutions. So what we did and what we do is basically say, okay, no, we're gonna strap on our lab coats, do the work that it requires, take advantage of some great work that has been done. Fortunately, plume rise, or the buoyancy of plumes, has been taken into account, and very, very intelligent and very, very committed people have done a lot of mathematical work to derive practical solutions to that one specific nonlinear problem, which is quite an accomplishment. And we've been able to leverage the theory, leverage the literature in order to apply it to our system in a way that maintains the requirements for robust and reliable performance while taking into account this piece of physics that's very, very important.
So let's like distill that down then. What you're saying is engineering and applied science, they're looking for efficient answers. Nonlinearity introduces a whole bunch of challenges. Mm-hmm. Oftentimes it's easier to keep your solutions linear, albeit at a lower level of precision. It's not nearly as accurate. In order to keep them linear, you oftentimes have to make assumptions about things that you're unable to observe because it's either unaffordable or not practical to collect those observations, meaning that you would know the true temperature of the compound that was being released, and thereby you could understand the buoyancy better, but not completely. So the point here is that if you take the time to spend the money or find a solution to navigate this, you'll actually dramatically improve the solution that you can get and the accuracy of your results.
That's right. And so one has to invest in that particular. But first you have to identify the importance of it, which we did. We identified the importance of this particular physical phenomenon. We're not just throwing physics into our modeling systems without any scientific guidance. So the scientific guidance comes first. To identify that buoyancy is a driving and determinant factor in our estimates of emissions came first. And then came the work of incorporating that into our systems.
But I think you're hitting on an important point, cost benefit, right? Yeah. And that's what everyone is really trying to get at. For instance, like when we talk about computational fluid dynamics with some of the folks on the team, we'll go after this. You could simulate something to the end of the earth, right? You could do
Mm-hmm.
incredibly tight spatial resolution or incredibly tight time increments. And in doing so, your computational resources go to the stratosphere. But like, how much increased precision are you really getting? And I think one of the important things that you and we in particular did was assess that this whole idea of buoyancy can be a huge driver in terms of allocating emissions correctly, quantifying them.
That's right.
Right. And I think that's the thing that we're always after is like, where do you see greater returns for engaging in the hard science? And when are you hitting a point where you're running a computational fluid dynamics simulation and you're saying, hey, this is costing us $10,000 to run for 60 minutes at one site. This is not an effective solution because it only yields X amount of benefit. Right. And so it's really going after some of these more beneficial or more efficient ways of navigating this problem. I guess just switching topics a little bit, like going back to your days at NOAA and thinking about numerical, weather forecasting, like where did you see this buoyancy idea come in a lot?
Oh, everywhere. No, so buoyancy and the motion of air by buoyant effects is fundamental and paramount to everything that happens in the atmosphere, specifically in the atmosphere that surrounds us, right? So we don't live at the elevation where jet planes fly, right? There's very different things are going on in that atmosphere, but in our atmosphere that is close to the ground, buoyancy is absolutely important. And similarly, methane being released from nearby surfaces is being released in that atmosphere, in the atmosphere that we care about, in the atmosphere that affects the way we breathe, the quality of life that we have, and if it gets hot, it's that atmosphere is the one that we experience, is the one that's sort of in the lowest 1 kilometer of the atmosphere is our little piece of that ocean of air. Yeah. That we care about. And buoyancy is dramatically important in that setting.
I always oversimplify it in that, like, you have the sun shining into the atmosphere, a portion of the air gets hotter than average, that air expands, it rises, and then there's other air that has to move in to fill that gap, per your discussion last time. In turn, that's where wind in part comes from.
Yep.
Right. And I don't think a lot of people really link up that wind is really solar energy.
That's right. 100%. We talked about energy a little bit and what might energize, things. And it's the sun. It's the sun heating up ground and elements on the ground. So, for instance, that's why our cities are hotter than the surrounding countryside. Why? Because our buildings are made up of materials that are much more effective at absorbing all of that energy that's being radiated down upon them. And that change in energy in the buildings translates into hotter surfaces. Those hotter surfaces are in contact with the air. That contact between the air and the surface transmits that energy over to the air. That gets picked up in the wind and transmitted into this atmosphere that we care about, creating bubbles. And these bubbles move that energy around and disperse it around and carry anything along with it, including methane. If it's present, it's going to get carried along in those motions that are inside of that boundary layer.
Awesome. Thanks, Jorge. I don't think that people fully appreciate how impactful something like density and buoyancy can be when you're trying to do something as seemingly simple as measure methane emissions.
Yeah, it's been a really great pleasure talking about all of the physics that is involved in how methane is dispersed in the atmosphere and all of the atmospheric science involved. As a particular passion of mine, we have an excellent team of engineers and scientists that have extensive training in computational fluid dynamics, which inherits from the experimental fluid dynamics of the last 100 years and all of that understanding. People that know atmospheric science, forecast verification, because what we're building is a predictive system for the quantification of methane at a given site, and using that to be able to get these emissions out. And so we have a wonderful team in place. We're working very hard to identify the correct way of tackling this problem, of answering this very difficult question of where did the methane come from and how much came from a particular source, so that we can stop it from leaking.
Awesome. Thanks, Jorge. Until next time.